Good evening and welcome back. Sorry for last week. I was not in Nagoya. So I'm going to recall what we have done 2 weeks ago. Okay, and the main part on what we really need is here. So I go quickly in this part. I introduce so we have seen the notion of immersion and then the notion of injective. And if you have an injective immersion, so it's a map from a manifold to a second one. So you look at the image and you call it a embedding. It's if it is homeomorphic when on this image you put the what is called the subspace topology. It means you put the topology that is inherited from N. Because you have a natural topology on this given by M, but it's not the most interesting one. So we say it's an embedding when this M on its image are homeomorphic, but when this one is embedded with a topology that you get from M. And I explained this last week, or 2 weeks ago. Then the thing which is very important and which helps us a lot is this notion of M submanifold property. And because this is a way, I use this ball, when we have a manifold in a bigger space, with this, what is called M submanifold property, you can check that this is a manifold. Of course, you need an ambient space which is bigger, so this is a result which is useful when you have a bigger space, but this is what happens in many cases. And by the way, I'm playing with a balloon again. You remember during the first lecture, we had a journalist who came and took a few pictures. The paper is somewhere, you can just circulate this paper. So they made an article, not only about these courses, but more generally. What is fun is there is a picture with me playing with a ball, but this is not the most interesting part. The most interesting part is that all students are watching very carefully at me playing with a ball. You can look at the picture. Probably they're more interested when I'm playing than when I discuss about more serious things. Okay. Okay, then we introduce this notion of germs at P. So what you should keep in mind, you have a manifold, you take a point P, and you look at all functions defined near P, and we make equivalence class when two functions are similar on a small neighborhood of P. If they are equal, we say that they're in the same equivalence class. It means you are really interested in only essentially what happens to this function very close to P. This is the notion of germs at P. And then we introduce this notion of tangent space. And today we will make the link between this abstract notion of tangent space and what we know from calculus 2 about tangent space generated by curves and tangent vector. So probably I remember this picture last time. I told you also for tangent space how we introduce in calculus 2, we make a curve on a surface, and then we take the tangent vector, and this tangent vector generates a tangent space. Today, we will make a link between this definition and what I just recalled. So the definition of the abstract tangent space is the set of all linear maps from this set of germs, so this equivalence class of function to R, which satisfy what is called the Leibniz rule. And I mentioned what it is last week. Okay, so this is a definition, the abstract notion of tangent space. What you observe is that you don't need an ambient space. You don't need something around your manifold. And then we took the example of Rm, and we observed that, oh, and by the way, I use xp for a tangent vector at P. And we observed that if you take this expression, which is known from calculus 2, V scalar product with a gradient applied to a function evaluated at P, then this expression satisfies the Leibniz rule on its linear. And it turns out that all, for Rm, for the manifold Rm, all tangent vector can be expressed like this. So we have a good representation of tangent vectors for Rm. And from this, we know that this is m-dimensional because we have m degrees of freedom. And there is a rather special notation, but we have to get used to it. It's coming from this. The basis is denoted by these partial derivatives evaluated at P. So d over dx1 up to d over dxm at P. It's a natural notation if you think about this expression. So this is a basis for the tangent space. And then the next thing I introduced, and I told you this is an easy exercise because you just need to be careful with the definition. If you have F between two manifolds, you can define two maps. One, so you have F of P here. And we have here the equivalence class of function. So the first map, the F star with the upper star, is sending the equivalence class of function defined here to the equivalence class of function here. So this is F upper star. And it's a homomorphism of algebra. I explained this last week. And the second one is now going from the tangent space here, the tangent space. Keep in mind still this idea of when you have a manifold, the tangent space is something tangent to it, even though it's not exactly the definition, but it's good to keep it in mind. The tangent space of this manifold at P is sent with a F star, but with a lower star to the tangent space here. And it's just a matter of checking the definitions. And this map is a homomorphism of vector space. So it transforms this vector space into another vector space. Homomorphism means it preserves the structure. So the first one, it's a homomorphism of algebra. So it preserves the multiplication. Also, this one is just a homomorphism of vector space. So it preserves the structure of vector space. Think about it. And it turns out that if this F is bijective, and also, so it's bijective and smooth in both directions, then this one on its inverse are homomorphism. When in this case, we say that F star is an isomorphism. So I stop here. And now what I want to do, I will consider this N as Rn. N or Rm. And why I'm going to do this? Because look, we already know a basis of the tangent space here. And with the information here, we are going to get a basis for the tangent space here. So that's the idea of what I'm going to do. And then we will make the link with curves. Again, if you have any question, you can ask me at any time. And don't forget, on the website, you can find some reference book. On the second website, you can find all the information you need. So I'm going to use this ID there to get a basis on the manifold M. So we consider the second manifold being equal to Rm. And I'm going to consider U phi, a chart for M. Remember what is a chart? So a chart is take a U, which is sent on part of Rn. So now this is part of Rn, as you usually represent it like this. And the image, it's a bijective function from, and I call it phi. This is a chart. And I consider also P inside U. Okay, then phi star. So the F is now phi. So phi star, if I just copy what is here, it goes from Tp of M, the tangent space at P for the manifold M, to T phi of P at Rm is a so I'm writing exactly the same. Is a homomorphism, but its inverse is also a homomorphism. And phi minus 1, so the inverse, put it like this. Now from T phi of P of Rm to Tp at M is also homomorphism. So we are in the best situation because the map phi is bijective. So now, so it means we have an isomorphism. And so I'm going to take the basis of Rm as the image of the basis of Rm as a basis for my manifold M. So it, yes, not long enough. Homomorphism. Thank you. So definition of this new basis, the family. So phi minus 1 star F. Of course, the first time you see this, it's a bit abstract, but then when you really play with this definition, it becomes more concrete. J, it's a J. And I consider this family J from 1 up to M. So look what I'm taking. I'm taking a vector. So this is Rm. It has a basis at this point. Probably I should do this part again. We have Rm, and this is phi of P. The tangent space has a basis, which is given by these vectors. This is a notation I use for this basis. And now I take it back by phi minus 1. So phi minus 1 is going in this direction. And I'm taking it on the tangent space at P for the manifold M. So the family defines a basis of Tp of M. And it has a name, it's called the coordinate frame. Its coordinates frame. This is good. We knew a basis on Rm. We take it on our manifold, and this gives us a coordinate frame. I want to emphasize something. The tangent space itself, how we define it, does not depend or is independent of any chart. If you look at the definition, I didn't use any phi for defining this tangent space, but a natural basis is given for any chart. So it's important to realize this. The tangent space itself is independent of any u and phi that you use to describe your manifold, but you get a natural basis, or you get one basis whenever you use a chart. Okay. Natural. It's not defined, but in the sense that, by construction, you have only one. Once you have a chart, natural in the sense that it's given by a certain formula. You don't have any freedom in this sense, natural. You have phi, and you take back the vector of the tangents, the basis of the tangent space here, back to the manifold. In this sense, it's natural. It's given by a certain formula. Okay. And let's just look at this, look abstract, but let's just see that, in fact, it's completely natural. because for f belonging to C infinity of P, so function defined just close to P, what is phi minus 1 star d over dxj P applied to f? Remember, an element of the tangent space is a linear map that you apply to a function. And now you look at how we define this, and you get that this is nothing but d of f composed with phi minus 1 over dxj evaluated at evaluated at phi. So probably I should, this is evaluated. I should do the picture again. The manifold P. This is phi. And we have a point phi of P. Let's make it bigger. A point P which is sent to point phi of P. A function f, it's difficult to represent a function defined on the manifold, but think about the temperature. The temperature is a one quantity which can be associated to any point of the manifold. It's a function from the manifold to R. This is a good example of a function defined on the manifold. So let's check. We have the tangent space, and we want to apply it on f. I use this formula, which is what we have defined. I get this, but just check that this is completely well defined in the sense phi minus 1 is a function from Rm to the manifold, and then you compose with a function defined on the manifold. So it means this composition is now a function defined on this with value in R, and you take a partial derivative. We know that we can take partial derivative for function on Rn, and we evaluate at this point. So this formula, I would say it's completely natural. And this is just by our construction. In the notes, I've put a few additional information about these kind of things. You can have a look if necessary. I will come back. There is even an exercise. I don't want to spend too much time. What we should remember, we had a natural basis on the tangent space on Rm. We bring it to the tangent space on the manifold simply by what we have developed, and we get natural formulas. Right? Now, as I said, I want to spend some time doing the relation with curves, because in calculus 2, and maybe it's more natural to think about curves and derivatives, the relations with curves. It's a bit long, but I think it helps for understanding. And I don't want to, remember, I don't want to be back to this situation where the manifold has to be in something bigger. I want always something which is intrinsic, so no ambient space. So we consider a parametric curve. You probably all know what it is. You have your manifold and a parametric curve. You have this is R, take a small interval, and you send it to a curve on the manifold, like if you describe a path on your manifold. So parametric curve C is, I will always take in on a small interval containing 0, and I will use n for the manifold. So this is a small interval around 0 from minus epsilon to epsilon, with C of 0 is a point P, which belongs, of course, to n, the manifold n. Right. And of course, epsilon is bigger than 0. But if you think about it, this is, so we have this small interval, let me this is already a map between two manifolds, because this interval minus epsilon epsilon is a manifold, and this parametric curve is also a map from a manifold to a manifold. So I can use what we have seen as map between manifolds. Now I'm going to set capital C for C of minus epsilon epsilon. So what is this capital C? It's just this figure. This is capital C. And assume, I need one small assumption, that C is a diffeomorphism on from this interval minus epsilon epsilon to C. What do I mean on what I cannot consider? I don't want to consider things like this. This wouldn't be bijective. But locally, I'm going to construct something very local. So I can always consider a small part where this interval is mapped bijectively to another interval on the manifold. I don't want to consider this. So I assume that the map is differentiable with the inverse also differentiable. It's a diffeomorphism. But locally, this is always possible. Okay. Then, what we can consider is, so it's a small c. And small c star of d over dt at 0. What is this object? This is basis of the tangent space, which is one-dimensional, tangent space at 0 of the manifold minus epsilon epsilon, right? I told you it's a manifold. So I can consider the tangent space, and if I respect the notation I have introduced, it should be this, it's only one-dimensional. And by taking this C with a star below, I get, so suppose we have 0, now this is P, I get a tangent vector. I represent it like I used to represent it, but it's not in a bigger space. So it's, by definition, this is a tangent vector. The tangent vector to C, be careful, it's a tangent vector of C at P. And observe, we can again get an expression if we apply it C star d over dt at 0 applied to F, because this is the way I should apply it. I should apply it to a function defined on the manifold. If we just look at what we get, this is d over dt of F composed with C evaluated at 0. And again, check that it's well defined. C is a map from this interval to the manifold. Then we apply F, which is defined on the manifold, on C. We take the derivative here, and we evaluate at the point 0. So this is an expression I want to keep. And we can, and more generally, I don't need to evaluate at 0. I can consider I want to consider C, small c, C star of d over dt evaluated at t. Where is this t? T has to be inside this small interval minus epsilon, or t inside minus epsilon, epsilon. is a tangent vector. A tangent vector. At which point is it a tangent vector? It's a tangent vector at C of t. If you look at it, if you look at the definition, it has to be a tangent vector at the point C of t, which is any point here. All right. Okay. So far, so good. Where is F, by the way? I apply it on a F. Can you tell me where is this element, or where does it live? If I want to be coherent, F is a function. I want to be coherent. It's a function defined on this image, just on this curve. So F is in fact in C infinity of P, but on C. It's a function defined only on this small curve. All right. Now I want to do something a bit more general, because remember, my aim is to think about the tangent space of this, so I probably need more than one curve. So I'm going to say, oh, around this point, we have also a chart. This I can call it U, phi, and we have a phi of P here. This is a chart. Okay? So we have this, not only a curve, but any point has a neighborhood which is mapped to an element of a subset of Rn, an open set of Rn. So I will also use this now. So I consider this chart, so let me introduce it. Let U phi be a chart with P inside U, and in fact, I will even ask a bit more, and even C inside included. What do I mean by this? You know, I take epsilon small enough, and I consider the image inside U by taking restrictions. This is not a big limitation. I consider this small curve inside U. So either I can take U big enough, or if I cannot take U big enough, I take a smaller interval. So I assume that the curve is inside U. Now we set Cj is going to be this guy, phi composed with Cj. What is this? Look, C is a map from here to here. And then, so I'm on this curve and I map it to, maybe I should even do this one bigger. This is Rm or Rn. We have the image of the curve because phi send me this curve on something in Rm. So I can consider the coordinates of this curve. So Cj is the j's coordinate of the curve, right? It's a local coordinate with this. And for j from 1 up to n, because it has, so every point which is sent here has n coordinates. This is probably C1, oh no, C2, and this is C1, the n coordinates. Yes. Sorry? I think I called this time the manifold n in my notes, so the dimension should be n. Check. I think this part I choose n for some strange reason. You know, I can call it with any name, as long as a manifold M should be of dimension M, a manifold N should be of dimension N. But I think it's coherent. Or if I did a mistake, please circle in the notes. Okay, so we have this picture. And then what I'm going to do, take F now. This is a key point in N. Be careful about this. I told you just before I had written a F which was living only on the curve. Now I take a F which still live on a neighborhood of P, but as a function on the manifold. Okay? Take in N. And I don't want to be only located at P. I want to be located at any point, so at C of T in N. So I want to consider a function defined at any point here. And then now we need calculus 2. And it's a very nice application of calculus 2. C star d over dt T applied to that. I want to compute this. And it's not a mistake to take a function defined on a big set because its restriction on the curve is still a smooth manifold. So this is well defined. And if you remember the formula I have written before, this is d over dt of f composed with c evaluated at t. Not only at 0, but at t. It's a composition. But now I'm going to do a small trick. I'm going to add phi minus 1 phi. This is just the identity, right? It's bijective. Okay, so I'm allowed to do this, and I'm even allowed to add parentheses because it's associative. Okay. It's magic. Okay, and then, you know, this is a first function, this is a second function, derivative with respect to one variable of a composition. We learned this in calculus 2. It's a derivative of the first function in a certain sense, evaluated at the second one, times the derivative of the second one. This is something we learn in calculus 2, how to differentiate this kind of thing. So if you remember calculus 2, this is a formula that you should remember, d of f composed with phi minus 1 over dxj, when I sum the partial derivative, evaluated at phi of c of t, which is the second part, times cj prime at t. Try to remember calculus 2. You have two functions. This function is from one variable, but with value in Rm. And then you take from Rm to R. So the derivative of this composition is this derivative. And then you differentiate each component. So this is Cj, which I have introduced here. Derivative with respect to the variable t evaluated at t. And now if we have seen already this expression before. I even gave a name to it, and I will recall it. From 1 up to n of, this is a number, Cj prime at t. This is just a number, so I take it as a coefficient. And this expression circled in yellow is what I called E. C of t applied to f. You can check in the notes. Okay, so what does it mean? Try to think about it. The tangent vector, which is defined by this expression, can be written or is equal to a linear combination of this tangent vector on the manifold with the coefficients given by this. So it means any curve define a tangent vector, which is what we knew from calculus 2 in a slightly different picture. But look, this is a tangent vector defined abstractly, and it gives us a linear combination of this tangent vector. Oh, in fact, no, I'm cheating when these are numbers. So I should not speak about tangent vector. I should forget the f. So it implies, just remove the f. It implies that c star d over dt evaluated at t, which is a tangent vector, is equal to this sum of j from 1 up to n, cj derivative evaluated at t times this ej c of t. Now, this is more precise because if you apply to f, you get numbers. So what you should keep in mind with this expression is that any curve, because we started with the curve, any curve defines a tangent vector by this relation here. So we are back. I wanted to spend this time because it's very similar to what we know from calculus 2. We know from calculus 2 that a curve defines a tangent vector, but with this image of a tangent vector in a space which is outside the manifold. But still, this image is correct once we interpret correctly these different things. A curve applied to a tangent vector. So this defines a tangent vector, which can be expressed as a linear combination of all these tangent vectors. So any curve defines a tangent vector by the formula here. So what we learn in calculus 2 is not different from this, except that it's more concrete. Now you can wonder, oh, do we have the converse? Because we know that these vectors here generate the vector space, which is tangent. Can we get a curve for any of them? And the answer is yes. We will see it in a few minutes. Okay. So I think this computation is important and nice. You should keep it in mind. Any question or remark? We have a notion of a tangent vector abstractly. It's still related with curves, like in calculus 2, by this formula. Yes. Cj is a component. Okay. You have the C1, C2 up to Cj components. So because the curve is living here, but I represent it on Rn, Rn. And we have its component. But look, these components depend only on one variable t. When you change t, you move on this curve, so the coordinate change. So I take this is a function of one variable. I take its derivative respect the only variable, and then I evaluate at t, it's a number, times this. So you have, it's a linear combination of tangent vector. Which function? Yeah, these are the, you have your manifolds. If I come back to the picture of calculus 2, you have a curve on this manifold, then you represent it on Rn. So you take a map of phi from this to Rn, and then you have coordinates of your curve. On a real map, take a path and it has coordinates. Okay, vector fields. As somebody just said before the lecture, vector fields are everywhere. And indeed, vector fields are everywhere. When you look at the weather forecast, you look at a vector field because at every point, you have the direction of the wind. So you have a map representing Japan. At every point, you have the direction of the wind. This is a vector field. It's a new type of function that we have not introduced. So we have to define the domain and the image. So what is the idea? At any P belonging to the manifold, we associate an element of Tp of M. And indeed, if you think, my balloon, where's my balloon? If you think about this, at every point, the tangent space should be represented by a plane. And what we do at every point, we associate one vector in this tangent space. So at a different point, we associate another vector in this tangent space and so on. So I put some pictures in the notes. It's a representation of a vector field. At every point, you associate an element of TPM, so of the tangent space. Of course, abstractly, this is complicated because this is a linear map, blah, blah, blah. But if you have in mind the image of calculus 2, then this is, you can represent it as a row inside the tangent space. And as I said, it appears quite at many places. The problem is how you define continuity or smoothness of a vector field. It's not completely trivial. There are different approaches, and one is going to be simpler. So how to impose continuity or smoothness? Why isn't it so easy? Because think about, again, my balloon. The image at two different points live in two different spaces, because at one point you have the tangent space, which is like this, but the next point is slightly a different plane. So the notion of smoothness is not completely trivial. So there is one way to do it. We introduce what is called the tangent bundle. So we introduce T of M, the tangent bundle. This is the name, tangent bundle, and what it is. T of M is given by just the union over P of Tp of M. This is not an easy object. Think about it. You take all planes which are tangent to the surface, and you take their union. It's not something so simple. But, so in some case, we can make, and this is not what I will do. In some case, we can make a manifold, or let's see differently. We can put the structure of a manifold on this very big space. I will not do it, and consider function which I'm going to call x from M to T of M. So if we do it, we can consider this is a manifold. If this very complicated space, I can put a structure of a manifold, then we have an application from M to this union of all tangent space. It's not easy. So I will take a different approach. Why? And why it's going to be simpler? Because remember, on each tangent space, we have a basis. On each tangent space, we have defined a basis, which is this coordinate frame. So I can use this basis on each of these tangent space, and then it will be simpler than this approach. So I will not go on with this. Yes?
The domain, like we partition the domain into the
Do you want to divide this? Yes, but still this object is going to be very complicated, even if you take some smaller piece of M, TP of your small. In fact, I'm never saying that M is all this. You know, you can always take a small part of it and call it M. A good part of a manifold is also a manifold. So I'm not saying that always M has to be this entire board. It can be just part of it. But no, taking a partition of M wouldn't help you so much. But yeah, in a sense, when I take charts, yes, I take a small part of it. You have a question or a remark? I don't know. I don't want to go in this direction. I'm not confident. I need to read more about this approach. The next approach is quite natural. So I don't know if it is always possible. You know, you need to put a topology on this space. And it's not easy because how, you know, you have these different planes. How do you construct open set? What? Okay. I'm not sure I can do it. So let's take a slightly simpler approach, because if we have our manifold, we have also charts. This is now my manifold is going to be M. So I'm going to have a U and a phi from these two parts of Rn. Okay. So I'm going to keep this in mind. So for any chart, U phi of M, okay, and for any P inside U, so I take P, the coordinate frame and I recall the notation, the coordinate frame is this EJ T, J from 1 up to M, is a basis, we know it, of T P of M. Okay. And we even have explicit expressions for this one in terms of phi. So I can, so then any xt, which is a tangent vector at P, can be written xp is equal to a sum j from 1 up to M of these EGP, and then we have coefficients alpha j of P. These are coefficients. These are coefficients. Any tangent vector can be written, this is linear algebra, any tangent vector can be written on a basis with some coefficients, right? And what, so this is just a number for a given vector field. These are n or m numbers. This is just an element of R. Okay, but then we can look I'm going to look at the following function. We can look at the function from Rm phi of u, take x goes to alpha composed with phi minus 1. Okay, I'll let you look at it. And look at this function. I want to move around different points here. So what I can do, I take some x here, go with phi minus 1, and then I look at this function alpha, which is, so I do this composition, phi minus 1 from Rn to the manifold, and then I look at this coefficient. So now we have a function from Rm to R. And for defining smoothness or anything, this is the best case. So now I can give you the precise definition of a vector field and its smoothness. So definition. And I will always work with smooth vector field, but for some applications, it's good to look at, let's say, continuous or once differentiable vector fields. So I'll give you a definition which is more general than what I need. So for R belonging to 0, 1, 2, up to infinity included, because I want to consider smooth, so it means C infinity vector fields. A vector field of class, this is the regularity of class CR on M, is a map X, this is a general notation, from the manifold to this tangent bundle, whose component alpha I should write probably, oh no, whose component alpha, this is correct, are of class CR in any coordinate frame. What does it mean that it's of class CR in any coordinate space, in any coordinate frame? Precisely, it means this map here, is of class CR. Everything is well defined. So I consider a map from X, a map X from the manifold to this tangent space. In every tangent space, you can look at the components with respect to a certain basis. So you decompose in a basis which is different in each of these tangent space, but you have a natural basis. Then you consider this map locally, as we have seen, and you assume that this map is CR or C infinity. So I define the smoothness locally thanks to these charts. So maybe this is what you had in mind when you mentioned partition. Indeed, whenever you have a chart, you can look at these coefficients given by this expression and assume that this expression is of class CR. And the class C infinity has a special name or has a special notation. So I want to introduce this notation. The set of all what we call it vector field of class C infinity, so the one with where this function is infinity is denoted by notation which is quite standard. It's a kind of curly X of M. You can see in the notes. It's a curly X like this of M. So at every point of your manifold, you associate a vector on the tangent space, and the smoothness is defined in terms of this coordinate frame. Any question? I know it's a lot of information, so try to get some pictures of this. Not only you, is there anybody else who has a question? Not always the same. Okay, I look, wait, is there a mistake? You're right. Wait. So if I consider just one of them, it's a number. So either I put a J here, or I should, you're right. Maybe there is even a mistake in the notes. I need to check. You're right. Either I take only one component and then its value in R, or if I want to consider all components simultaneously, it's probably with M. You're right. So please let me know later if there is a mistake in the notes. Yes. Either it's a vector in Rm, if we look at the M coefficients, or we can look at each of them individually. Okay. Yeah, it's probably better like this. That's all. So I think now it's correct. This, I don't put a J. So now the family is in Rm, we have M coefficients. Or if I put only one coefficient, it's in R. No, the alpha, so it's from the manifold. I mean, alpha is a function defined on the manifold to Rm. You're right, manifold to Rm, but I look at it in, I cannot define differentiability. I need to look at it with charts. And then I do this composition, and this composition is from Rm to Rm. Yeah. Okay. Now, I want rather quickly to say a few words about this set, because because it has some properties which are not completely trivial. So remember, vector field, keep this idea of the wind on a map. It's a function from the manifold to the tangent space at every point. So structures on, and I receive a report on this, but it's not correct. So it's not completely trivial. Structure on. The first structure, which is, maybe this is slightly too, what I'm just going to write here is maybe slightly too advanced for first year. 1 point is a bit difficult, but still. First, it's a vector space. So what means it's a vector space? It means if you have two elements of this type, when you evaluate them at 1 point, this is nothing but this plus this one. This is quite simple. And in fact, you can even multiply by a lambda. And I mean, you need to check that, but we have already seen that the tangent space is a vector space. So you just use, this is the addition in Tp of n. So you check that you can do the addition of two functions. I define the addition of two vector fields locally. In fact, this is a definition. it gives you a vector space. The second structure, which is probably something new, it's a module, it's called a module over C infinity of M. So what does it mean? Take X, a smooth vector field, and take F, a smooth function on the manifold. And what can you do with these two objects? You can multiply them. You can set fx, so it's something new, evaluated at P is f of P xp. So how you should understand this, you have a function x which associate to any point a vector. Now each of these vectors, you can multiply them by a scalar, right? You just take the vector and you multiply it by 3. But the next one, or next to this point, you can multiply it by something slightly different. So you take this vector and you multiply it by a number, and you do this smoothly on the manifold. So this gives you what is called a module. So it means you can multiply. This is a multiplication of x on the left. It's important on the left. I take it before the left by an element of C infinity of M. And indeed, these vectors which are tangent, you need to change. If you multiply them by a scalar, you need to do this smoothly. Otherwise, the result will not be, this guy will not be a smooth vector field. So this is the second structure. And the third one, it's a Lie algebra. I already mentioned this in another course of a group. It's a vector space, a module, and it's a Lie algebra. So what does it mean? It means, and then I will define it, it means they exist. And we denote it by a certain notation. We denote it by this bracket. It's a function which takes two elements, so two vector fields, and associate a new one. So you take two vectors, and you associate a new one, satisfying some relations. There are three. So I just give you the abstract definition of a Lie algebra. And then I tell you what is this in this case. So what it satisfies, one, it's linear in each entry, which means I just write one, alpha x plus beta y z is the same as alpha x z plus beta y z. And the same if you take x alpha y plus beta z is the same as alpha x y plus beta x z. This is the linearity in each argument. Alpha, beta are just real numbers. Second property, it's anti-symmetric. Anti-symmetric. So it means if you exchange x and y, you get a minus sign. It's minus y x. So this is a notion of antisymmetric. If you exchange the two arguments, it gives you a minus sign. And the third one is what we call the Jacobi identity. Which is x, y, z. So it's a double bracket y, z, x plus z, x, y is equal to 0. How you remember this? Observe it's always x, y, z. You keep the order x, y, z, then it is y, z, and you start again x, and the last one is z, x, y. So you keep the ordering like this, and it makes 0. So this is a Lie algebra, the structure of a Lie algebra, which appears at several places. It's a map taking two elements and sending it to a third one, satisfying these three things. How is it defined? I just gave you the abstract structure. I need to tell you how to define this. It is defined by, so x, y applied to a f evaluated at p. Or maybe I should not write evaluate at p like this. I should put a small, yeah, the same maybe. Okay. It's given by x, y, p, f, and this is no, x. Okay, it's not completely trivial. It looks simple, but please. What is this object? Or what is this object? Can you tell me? I haven't introduced this in this way. X, a vector fit at every point, it associates. So remember xp, let's recall xp, it's from this C infinity of p to R. So now what is this? You need to take f in C and infinity of m. That's okay, because at every point p, so this xp, in fact, this is a function. I'm claiming that this is a new C infinity of m. Why? Because look, at every point p, you associate a number. When you apply it to a function, you get a number. So if you take this collection of numbers, indeed, it gives you a function on the manifold with value in R. So if you think about it, you can interpret x applied to f as a function on the manifold. But it's a slightly different interpretation. It's for f defined on the entire manifold. This is a new function applied, defined on the manifold, and you can take now, because it's smooth at any p, you can apply yp. And the same for this expression. So in fact, these guys are even defined separately. You can define them separately. The problem is if you define them separately, it will not satisfy. Remember, a tangent vector has to satisfy Leibniz rule. And if you take only one of them and try to check Leibniz rule, so if you take this expression, you will not get it. You really need this difference. So I told you it's not a trivial exercise. And it's worse, but maybe not for first year. for second or for third year or for master student, try to fully understand this and check why it's really a Lie algebra. I'm not sure we will really use it later. No, probably we will use it, so I will repeat it when necessary. But it means this set, curly X, which is a set of functions on the manifold taking value at every point as a vector, has three structures. It's a, or it's no more. It's a vector space. It's you can multiply by a function, so it's a module. You can multiply on the left, so you change the intensity, and it has this additional structure of a Lie algebra, which is not completely trivial. All right. Any question? So yeah, this is something we can work on it and get some feeling, but it's not completely easy to understand it. But if you look at the reference book, the exercise is done and you can get something. Okay, now let me just do a picture. Maybe you have already, or probably you have already seen some vector fields. So vector field, remember, at every point it associates a tangent vector. This is a vector field on R2. And you have probably seen also some curve like this. And then your vector field is supposed to be tangent everywhere. What is this red curve? What is this? This is an additional thing because look, the vector field is just this collection of a row. What is this curve? This is what I need to tell you now. And at the very beginning, or at one point, I told you we associate to any curve an abstract tangent vector. And I told you there is a converse. Up to each vector, we can associate a curve. But I told you we will look at this later. So this is part of what I'm going to say now. So I want to describe what is this red curve on a vector field. And this is the next section, which is called vector fields on flows. Vector fields and flows. So let me directly tell you the statement. And by the way, if you are in physics, you probably know that there are this theorem of existence of solutions of differential equations. In fact, this topic is based on solutions of differential equations. So let me tell you directly a result. M, a smooth manifold. There is an exercise about this solution of differential equation. And X is precisely a smooth vector field. So at every point, you associate a vector in a smooth way. So given at any point belonging to the manifold exists, epsilon bigger than 0, it will give me an interval and a parametric curve which I'm going to call C with the index P. We will see why. From minus epsilon to M with C of 0 is equal to P. And what do you expect? The derivative is derivative of the curve is something that we want. And C P star of d over dt at t is equal to x for any t. Okay, what is the meaning? We're in this situation. I told you most of my pictures are, in an ambient space. But everything, if you look at it, is independent of the ambient space. And I have an interval minus epsilon. So it says, take a manifold. My favorite manifold. Take a smooth vector field. For example, this if the manifold is flat, or take different vectors on this manifold. Then choose one point. In the manifold, I choose P. There exists an epsilon bigger than 0 on a parametric curve. So this is a parametric curve. So the parametric curve is from this interval to the red. This is index P, which associates the point 0 to P, such that we have seen a curve define a tangent vector. So such that the tangent vector associated with the curve, or defined by the curve, is equal to this given vector field. So this is the correct picture. I tell you there exists a curve such that the tangent vector are exactly this vector field. So in particular, if you just look at 0, not put my ball. In particular, so if I just look at C T star of d over dt at 0, this is x 0. No, x of p, sorry. It answers the question for what I had not shown before. For given vector, there exists a curve such that its tangent, the tangent vector defined by this curve is this vector. So this is a converse, but what I'm saying here is much stronger because this is the result just at one point. It is just at this point, it says, if you give me this tangent vector, I can construct a curve which has its tangent vector equal to this xp. But in fact, I can do much more. I do it on this entire interval. And the proof of this is based on solution of differential equation. Yes? No. No, this is a good point. Why epsilon, epsilon? Everything is local. You don't know your manifold. You may have some holes or you may have different things on your manifold. So you can never be sure that this interval is big. And indeed, I'm coming to this. Sometimes we can extend it. And I haven't written unique, but in fact, and here I could write and a unique parametric curve. But this unique has to be understood in the following sense. If by chance you can take a bigger interval, so if it is meaningful also on a bigger interval, on the intersection, there is only one solution. But of course, if you take a bigger interval, it means that the other curve is, this part of the curve is slightly bigger. So you cannot speak about uniqueness because you have two different objects, but the uniqueness here is in the sense that there is only one solution on the intersection of the two domains. So one domain is a big domain, another one is a short one. You get two different curves, but on the intersection, they are the same. But indeed, the notion of extending to a bigger interval is an issue. Okay, and I'm coming to this. And let me tell you a name, the curve CP is called an integral curve. This is the name, an integral curve, or an orbit. So whenever we have such a smooth vector field, we can construct, and in fact, we have many, we can construct different integral curves. And we will see this in a second. And by the way, this expression is also written, and maybe this is more intuitive. The left-hand side, we are going to write it, but it is just a notation. Precise meaning of the left-hand side is the one above, but it's a notation which is convenient because this reminds us calculus 2. Derivative with respect to time of this function is this vector field. But be careful, for this, I don't need any ambient space. Okay, and a remark which is quite trivial on this picture, even if it's going to be not so clear. Look, I started at the point P. Now, if I move to a new point, this is C. This point is going to be Cp of S. And then I can move to another point, which is Cp of S plus T. So first I move here, and then I move here. It's the same as this C, the curve associated to C of S T. Because as long as it has a meaning, starting at this point and moving along this curve time S plus T is the same as moving to this point. And now you define the new integral curve from here, and you go up to here. So this is C, starting here up to T. This is a T. This is a remark. And again, this is solution of a differential equation. One has, I just copy what we have on the left. C of Cs of T is Cp. In fact, I should write Cp, sorry. If I want to be precise, here I should put a P. Because it is along the curve starting at P, we go up to a time S, we get Cps, which is this point, and then we continue. So Cp of S at time T is Cp at T, S plus T, whenever it's defined. Of course, I say whenever it's defined, because if I take it for too long, I will go outside of the interval. Whenever. And a second remark, and it answers your question. One can look for the longest interval on which Cp is defined. So I extend this epsilon from minus epsilon to epsilon, so we can look for the longest interval on which Cp is defined, and it is denoted by simply IT. I is for interval, so you can look, I want to know if I can extend this curve, and what is the longest interval which defines this curve. Okay. But as I already mentioned on this picture, this is for one point P. Most probably, I'm interested in something more. Let's say I take a neighborhood around P. What can I say about the other curves? Are they similar? And this is a notion of flow. What happens if you take another point and you construct the other curves? How do they behave? Do they behave very differently, or do they stay in the same neighborhood? So this is something which is of interest. So it's a dependence on the initial point P. I took it for one P. Now what happens if I take different P? Is there any question or remark? Again, the last thing, which I will not finish, but the last thing is to speak not only about one curve, but a family of curves like this. So let me define a certain thing first. Let's W, it's the union over P belonging to M of IP times T. What does it mean? You should think like this. For a second, suppose your manifold is very simple, because otherwise I cannot make a nice picture. This is my manifold. I take a point P, and I look at the longest interval I mentioned. So I take in this direction, this is IP. And then you take a different point, and you look again at this interval. This is P prime, I, P prime. Okay, so at every point P, you associate this interval of time on which you can, the maximum interval of time, right? And you get this union over P belonging to the manifold of this interval times P, and you observe that this is in fact an element of R times M. Why? You have, it's, in my picture, it's two-dimensional, time in this direction, M in this direction, all right? But of course, if you make a more complicated manifold, the picture is more complicated. And it turns out that this set, it's not so important, but this set W is open in R times M. Why? Because each interval is an open set, but this is not so important. And you can wonder one thing, and there is a small problem. Suppose your manifold is very long. You know that at each point, you have a certain, the theorem tells you there exists a small interval. But what could happen is that these intervals are becoming smaller and smaller. So you can wonder, oh, if I want to have something global, I have a small problem. And we are going to solve this problem next time, because locally, if you always take something locally, you can draw a rectangle. Even here, I can draw a small rectangle, very small, which contains all these small intervals. Which is contained in all these small intervals. Okay, let me just give you, I give you the next definition and we stop there. What is the notion of flow? In the title, we had the word flow. So what is a flow? The last definition, and then I stop. A flow, or it's also called a one parameter group. It's a group action. A group action on M is a map. It's a C infinite map. It's a C infinity map, so it's a smooth map. And I'm going to use theta from this strange space W to M, satisfying. So remember, W is made of two things. You have a part, something belonging to T on a point on the manifold. So it satisfies two conditions, theta of 0p. It's always p, which means your function at the time 0 is exactly p, or any p belonging to M. And the second condition is something essentially I mentioned here. I'm just rephrasing, in fact. Theta of T, theta of SP is equal to theta. What is the link with what I mentioned before? In fact, theta of TP is nothing but CP of T. Why I change the notation? I simply want to have more freedom because look, before the P was index related to the initial point. Now I want to have two coordinates. I want to have the time, but also precisely this dependence on P, be able to change. So instead of having this dependence as an index, I define a function of two variables, one variable which is a time, and the second variable which is a point on the manifold. And this is nothing but the fact that at time 0, you are at the point P, and then you have this relation that I always mention, going from P to along the curve S plus T is the same as first going to S from P, and then you move the time T. So this relation is exactly the same as this one, but the notation is slightly different. And so next week, we will start again with this flow and describe what we have, this flow on a manifold.